There are few ideas in physics treated with more quiet reverence than the conservation of energy. It is spoken of as if it were not merely a rule, but a guarantee, a promise written into the fabric of reality itself. Across centuries of scientific progress, through revolutions that shattered older worldviews, this single principle has remained untouched. Energy can neither be created nor destroyed, only transformed. That sentence is repeated so often that it begins to sound less like a conclusion and more like a truth that never required proof. From classrooms to laboratories, from textbooks to research papers, energy is presented as the thing that makes the universe go. Motion happens because energy is present. Heat flows because energy moves. Stars shine because energy is released. Even emptiness is no longer empty, because vacuum energy is said to fill space itself. When physicists describe why anything changes at all, energy is almost always the answer. This belief is so deeply embedded that it shapes the way we speak. We talk about energy being spent, energy flowing, energy powering systems. We describe stars as engines and galaxies as machines. We imagine the universe as something that started with an enormous supply of energy and has been gradually using it ever since. In this picture, reality is a vast process of redistribution, a long cosmic transaction where energy changes form but never leaves the books. It feels natural to think this way. After all, energy appears everywhere. A moving object has kinetic energy. An object held in a gravitational field has potential energy. Heat is energy spread among countless microscopic motions. Chemical bonds store energy quietly until they release it. Light itself carries energy across the void. By the time modern physics arrived, energy seemed to be hiding behind every phenomenon we could measure. Then came the most dramatic step of all. Matter itself was revealed to be energy in disguise. Mass and energy were no longer separate concepts, but two expressions of the same underlying quantity. With that realization, energy stopped being something objects carried and became something objects were. A stone was no longer just a chunk of matter. It was a reservoir of energy waiting, in principle, to be released. At that moment, energy achieved its highest status. It was no longer just conserved, it was fundamental. Or at least, that is what we assumed. Because energy appears in every successful theory, we rarely stop to ask why. We treat its conservation as evidence that it must sit at the deepest layer of reality. But conservation alone does not prove fundamentality. An accounting rule does not tell you what creates the system being accounted for. It only tells you that something remains balanced within it. This distinction is subtle, but it matters. We have grown accustomed to explaining change by pointing to energy, but explanation is not the same as origin. Saying that energy causes motion does not tell us why energy itself exists, or why the universe is structured in such a way that energy conservation holds at all. The confidence we place in energy comes from its success. Every time a theory works, energy is there. Every time predictions match observations, energy balances out perfectly. That success has trained us to stop looking deeper. We rarely question whether energy is the driver of reality, or merely a quantity that emerges once reality already has structure. And yet, cracks appear the moment we turn our attention to gravity. Gravity is everywhere. It shapes planets, stars, galaxies, and the large-scale architecture of the cosmos. It governs the motion of everything with mass and energy, including energy itself. Without gravity, there would be no stars to burn fuel, no galaxies to organize matter, no long-lived structures at all. If any phenomenon deserves to be called foundational, gravity seems like a strong candidate. But gravity does not behave the way energy does. You can store energy in a battery. You can localize it in a region of space. You can measure how much of it passes through a surface or is transferred from one object to another. You can watch it dissipate, dilute, and degrade. Energy follows rules that make it countable and trackable. gravity refuses to cooperate with this picture. A planet can orbit a star for billions of years without gravity weakening. Gravity does work without being spent. It shapes motion without flowing from one place to another. Attempts to define a precise gravitational energy density lead to ambiguities and coordinate dependent descriptions. In the very theory that describes gravity most accurately, general relativity, there is no unique way to say where gravitational energy is located. This should make us uneasy. If energy is the currency of the universe, gravity does not seem to pay with it. Gravity influences energy, directs it, confines it, and organizes it, but does not behave as if it were fuel being consumed. It acts more like a rule than a resource. At this stage, most explanations quietly change the subject. Gravity is said to have energy in some indirect sense, or the problem is dismissed as a technical detail. But technical details matter when they refuse to go away. The inability to treat gravity like other forms of energy is not a minor inconvenience. It is a signal that something about our hierarchy of explanations may be backward. We have assumed that energy runs the universe and that gravity is just one way energy manifests. But what if that assumption is wrong? What if energy only makes sense because gravity and space-time already exist? What if gravity is not powered by energy at all, but is instead the framework that makes energy meaningful? This idea feels unsettling because it challenges a belief that has worked for so long. But history shows that the most productive moments in physics occur when success itself becomes suspicious. When an idea explains everything too smoothly, it is often hiding a deeper layer beneath it. Energy conservation has earned our trust, but trust is not the same as understanding. And as we will see, the moment gravity enters the story, the idea of energy as the engine of reality begins to look less like a foundation and more like an emergent bookkeeping rule written on top of something far stranger. The deeper we look at gravity, the more the language of energy begins to strain. In classical physics, gravity is treated as a force that does work, yet unlike every other force, it never seems to draw down a reserve. A falling object accelerates, gains kinetic energy, and yet the gravitational field does not weaken in response. Nothing is consumed, nothing is depleted. The same gravitational influence remains, unchanged, ready to act again and again without cost. This already sets gravity apart, but the real fracture appears when gravity is examined through the lens of modern physics. In general relativity, gravity is no longer a force in the traditional sense. It is the curvature of space-time itself. Matter and energy tell space-time how to curve, and curved space-time tells matter how to move. This is not just a poetic description, it is the actual content of the theory. In this framework, gravity does not push or pull. It does not transmit energy from one object to another. Instead, it reshapes the geometry in which all motion occurs. Objects follow paths determined by that geometry. Motion happens not because energy is spent, but because the straightest possible paths in curved space-time are not what our intuition expects. Here is where the idea of gravity as energy truly breaks down. In general relativity, there is no single, universal way to define gravitational energy. You can write expressions that resemble energy, but they depend on how you choose your coordinates, change your point of view, and the value changes. Something that depends on perspective cannot be a fundamental substance in the same way kinetic or thermal energy is. This is not a mathematical inconvenience. It is a profound statement about what gravity is. If gravitational energy cannot be localized, cannot be uniquely defined, and cannot be separated cleanly from space-time itself, then calling it energy may be a category mistake. And yet gravity governs the evolution of the universe more than any other interaction. It determines how matter clumps, how stars ignite, how galaxies form, and how cosmic time unfolds. Without gravity, energy would have nowhere to gather and no structure through which to flow. This forces an uncomfortable question. If gravity controls energy everywhere but cannot itself be treated as energy, then what is energy actually doing? Energy, as we use it, describes the capacity for change within a given structure. It tells us how motion, heat, and work behave once space-time and its geometry are already in place. But it does not explain why that structure exists or why the rules of motion are what they are. Consider a simple example. A ball rolls downhill. We say gravitational potential energy is converted into kinetic energy. The accounting works perfectly. But what actually determines the downhill direction? It is not energy, it is geometry. The slope exists because space-time around the mass is curved. Energy bookkeeping describes the motion, but curvature defines the path. Remove the curvature, and the concept of potential energy loses meaning. There is no downhill, no preferred direction, no stored capacity waiting to be released. Energy requires a landscape to make sense, and gravity provides that landscape. This inversion is subtle, but it changes everything. Instead of energy driving gravity, gravity may be defining the conditions under which energy can exist and be conserved at all. This idea becomes even more striking when we consider the universe as a whole. The total energy of the universe is not clearly defined. In an expanding space-time, global energy conservation becomes ambiguous. Energy can appear to decrease or increase depending on how space-time evolves. Photons lose energy as the universe expands, not because they transfer it somewhere else, but because the geometry they move through changes. If energy were truly the engine of the universe, this behavior would be deeply troubling. Engines do not lose fuel simply because the stage expands. But if energy is a contextual quantity defined within space-time, then its behavior makes sense. The rules that govern energy depend on the geometry in which it is measured. This is not a fringe interpretation. It is built directly into the mathematics of general relativity. Energy conservation holds locally, where space-time can be treated as approximately flat. But globally, across the evolving universe, the concept becomes slippery. Gravity, meanwhile, remains unbothered. Space-time continues to curve. Structure continues to form. Galaxies assemble, stars ignite, and complexity emerges, even as energy accounting becomes less clear. This suggests that gravity is not just another player obeying energy rules. It is the arena in which those rules apply. The more carefully we examine this, the harder it becomes to maintain the traditional hierarchy. Energy explains processes within space-time. Gravity explains the shape of space-time itself. One describes transactions. The other defines the board on which the game is played. And yet we still speak as if energy is primary, as if gravity is something energy does. That habit persists because energy is familiar, measurable, and intuitive, while space-time geometry feels abstract. But intuition is not a reliable guide to fundamentality. At this point, a new possibility begins to emerge. What if gravity is not powered by energy at all? What if gravity is the structure that allows energy, motion, and even time to exist as meaningful concepts? If that is true, then energy conservation is not the deepest law. It is a consequence, a rule that emerges once space-time has certain symmetries. Change the structure, and the rule changes with it. This would mean that the universe does not run on energy in the way we casually imagine. It would mean that energy is not the engine, but the bookkeeping system that becomes useful only after the engine is already in place. And that realization sets the stage for an even more radical shift, because once gravity is understood as geometry rather than force, the question changes. We no longer ask how gravity uses energy. We begin to ask whether geometry itself might be the true driver of reality. If gravity is geometry, then the language we use to describe the universe has been quietly misleading us. We have been asking how much energy is available, how it flows, and how it transforms, while ignoring the deeper question of why there is a stage on which any of that can occur. Geometry does not need fuel. It does not burn, decay, or dissipate. Geometry simply is, and once it exists, everything else must obey it. This realization forces us to confront a hidden assumption that has guided physics for generations. We tend to believe that motion requires energy input, that change demands expenditure, that time advances because something is being used up. But geometry contradicts this intuition. In curved spacetime, motion can occur without any force pushing and without any energy being spent. Objects move because the straightest possible paths are no longer straight in the way we imagine them. A satellite orbiting Earth is not constantly burning fuel to stay aloft. It is following a path dictated by spacetime curvature. The motion persists not because energy is continually supplied, but because the structure of spacetime allows that motion to exist indefinitely. Energy describes the motion, but it does not generate the rule that permits it. This distinction becomes even clearer when we consider clocks. Time itself flows differently in different gravitational environments. A clock closer to a massive object ticks more slowly than one farther away. This is not because energy is being drained from the clock, but because space-time geometry has changed. Time responds directly to gravity, not to energy flow. If energy were the true engine of the universe, we might expect time to be governed by energy gradients. But instead, time responds to curvature. Geometry sets the pace. Energy merely plays out within the rhythm that gravity establishes. Once seen this way, the universe begins to resemble something less like a machine and more like a rule-based structure. Machines consume fuel. Rules do not. Rules constrain what is possible and what is forbidden. They shape behavior without being diminished by use. Gravity behaves like a rule. It does not weaken when it organizes galaxies. It does not diminish when it binds stars. It does not fade as it sculpts the cosmic web across billions of years. It imposes order without expenditure, structure without cost. Energy, by contrast, always appears to be contextual. It is defined relative to motion, position, and geometry. Remove the geometry, and energy loses meaning. Without space-time structure, there is no kinetic energy, no potential energy, no trajectory to speak of. This inversion is subtle but profound. We have treated energy as the thing that causes motion, and gravity as something motion does. But the evidence points in the opposite direction. Gravity defines the arena. Energy describes what happens inside it. The reason this reversal feels so uncomfortable is because energy is easy to count and geometry is not. We can measure energy with instruments. We can assign numbers to it. Geometry, especially space-time geometry, is abstract. It requires mathematics rather than meters. But ease of measurement does not determine depth of explanation. Historically, physics has often mistaken what is easiest to quantify for what is most fundamental. Temperature was once thought to be a basic substance. Heat was treated as a fluid. Only later did we realize these were emergent descriptions of deep emotion. Energy may be undergoing a similar demotion. This does not mean energy is unimportant. Far from it. Energy remains an extraordinarily powerful concept. It allows us to predict outcomes, design technology, and understand processes across scales. But importance is not the same as primacy. Energy may be the language of processes. Gravity may be the grammar that makes the language possible. If that is true, then the universe is not powered in the way we imagine. It is not running down like a battery. It is unfolding according to geometric rules that do not age, decay, or exhaust themselves. Energy moves things, but gravity defines what movement means. This reframing opens the door to an entirely different way of thinking about reality. Instead of asking how much energy the universe has left, we might ask what structures space-time allows. Instead of viewing gravity as one interaction among many, we might see it as the underlying framework from which interactions emerge. And once we take that step, a deeper question inevitably follows. If gravity is structure rather than fuel, and if energy is secondary rather than fundamental, then what truly drives change? What gives the universe direction? What makes time flow forward instead of backward? The answer does not lie in energy at all. It lies in gradients, in asymmetries, and in the quiet, relentless tendency of systems to explore what is allowed by the geometry they inhabit. The moment gravity is examined without habit or assumption, it begins to feel out of place among the other ingredients of physics. Every other form of energy behaves like something that can be counted, transferred, and localized. Gravity does not. It resists being bottled into a region of space. It refuses to sit still inside equations the way kinetic or thermal energy does. The deeper the theory, the more gravity slips through the cracks of the energy-based picture we rely on. In everyday physics, we speak as though gravitational energy is just another entry in the ledger. An object high above the ground has gravitational potential energy. As it falls, that potential energy turns into kinetic energy. The numbers balance. Nothing appears strange. But this neat accounting hides a deeper problem. The gravitational field itself does not lose anything in the process. It does not weaken. It does not drain. It does not show any sign that energy has flowed out of it. A stone can fall today, tomorrow, and 1 billion years from now, and gravity will behave exactly the same way every time. If gravity were a reservoir of energy, it would be exhausted. If it were fuel, it would run out. Instead, it persists unchanged, shaping motion endlessly without cost. This is already different from every other interaction we know. An electric battery empties. A chemical reaction consumes reactants. A star exhausts its nuclear fuel. But gravity shows no such bookkeeping. It organizes motion without depletion. It performs work without payment. The discomfort deepens when we try to define where gravitational energy actually resides. For most forms of energy, this question has a clear answer. Kinetic energy belongs to moving objects. Thermal energy resides in microscopic motion. Electromagnetic energy can be localized in fields and waves. You can point to a region of space and say how much energy is there. With gravity, you cannot. In the framework of general relativity, there is no unique gravitational energy density. You can write expressions that resemble energy, but they depend on the coordinates you choose. Change your perspective, and the energy appears to move or even disappear. Something that changes when you change your viewpoint cannot be a fundamental substance. It is a description, not a thing. This is not a minor technicality. It is a structural feature of the theory. Gravity is not something happening within space-time. It is space-time behaving in a particular way. Asking where gravitational energy is located is like asking where the energy of a coordinate grid is stored. The question itself assumes the wrong category. This is why gravitational waves are so conceptually subtle. They carry energy in a sense, but that energy is not localized in the same way as electromagnetic radiation. Even here, gravity refuses to behave like a normal energy-carrying field. The closer we look, the more gravity behaves like geometry expressing itself dynamically, rather than like fuel being transported. This creates a striking asymmetry. Energy responds to gravity. Clocks tick differently. Light bends, paths curve. But gravity does not respond to energy in the same way energy responds to gravity. Gravity does not weaken as energy flows. It does not drain as work is done. It remains as strong as ever, shaping the future without cost. This alone should force a pause. If energy truly runs the universe, then the dominant large-scale influence should obey energy-like rules. It should be conserved, transferable, and exhaustible in principle. Gravity obeys none of these expectations cleanly. Instead, it sets the conditions under which energy behaves the way it does. Consider again the idea of gravitational potential energy. It is not stored in the object. It is not stored in the field in any localized way. It is a relational quantity defined by the configuration of spacetime itself. Change the geometry, and the potential energy changes. The energy description depends on the structure, not the other way around. This dependence is the key clue. Energy descriptions require a background. They require a notion of distance, time, and motion. Gravity defines all three. Without gravity or something like it, there is no meaningful concept of potential, no preferred directions, no gradients to exploit. Energy cannot even be defined without a stage on which it can be measured. What we call gravitational energy is therefore not energy in the same sense as other forms. It is a shadow cast by geometry when we insist on using energy language to describe motion. It is a convenient fiction, not a fundamental substance. This realization reframes gravity entirely. Gravity is not participating in the energy economy. It is enforcing the rules of the economy. It tells energy how it may move, where it may gather, and how it must evolve without itself being spent. Once this is understood, the traditional picture begins to wobble. We have assumed energy drives change and gravity merely responds. But the evidence suggests the opposite. Gravity shapes change, and energy is the accounting system we use to track what happens within that shape. This does not diminish energy, it repositions it. Energy becomes a measure of what is possible within a given geometric structure. Gravity becomes the structure itself, and if gravity is structure rather than fuel, then its role in the universe is far deeper than we have allowed. It is not just another interaction. It is the framework that makes interaction meaningful. The implications of this shift deepen when we stop thinking about gravity as something that happens in space and begin thinking about it as something that defines space. In general relativity, space and time are not passive containers. They are active participants. They stretch, curve, and respond, and gravity is simply the name we give to that behavior. Once this is accepted, the idea of gravitational energy begins to dissolve even further. In ordinary physics, energy is something that exists within space-time. It occupies locations, flows along paths, and changes with time. Gravity does none of these things in a straightforward way because gravity is space-time. Trying to assign energy to gravity is like trying to assign mass to the shape of a landscape. The hills and valleys guide motion, but they are not objects that move energy around. This is why every attempt to write down a true gravitational energy density fails to produce something universal. You can define quantities that look like energy in special cases, or at great distances, or under specific symmetries, but there is no general answer that works everywhere. The absence of a unique definition is not a gap waiting to be filled. It is a signal that the concept itself may be misplaced. Gravity does not live inside space-time the way fields do. It is space-time expressing structure, and structure does not need to be fueled. It constrains motion simply by existing. This becomes especially clear when we consider how gravity operates over cosmic timescales. Galaxies form, merge, and evolve over billions of years. Gravity organizes matter continuously, relentlessly, without any sign of fatigue. There is no gravitational exhaustion. There is no cosmic budget being spent. The same curvature continues to guide motion long after the energy that initially lit the stars has been radiated away. If energy were the primary driver, we might expect gravitational influence to weaken as energetic processes play out. But the opposite is observed. As the universe evolves, gravity becomes more influential, not less. Matter clumps, structures deepen, curvature becomes more pronounced in localized regions. Gravity shapes complexity, while energy gradients flatten. This reversal is crucial. Energy tends to spread out. Gravity tends to pull together. Energy differences smooth away. Gravitational structure sharpens. If energy were in charge, the universe would quickly become featureless. Instead, gravity continually creates new structure, new gradients, and new arenas in which energy can act. This tells us something profound about their relationship. Energy follows gradients. Gravity creates them. A river flows downhill because of gravity, not because the water carries energy. The energy description explains how fast the water moves and how much work it can do, but gravity defines what downhill means in the first place. Without the slope, the concept of flow collapses. On cosmic scales, the same logic applies. Energy moves from hot regions to cold ones, from dense regions to sparse ones, from ordered forms to disordered ones. But gravity is responsible for the very existence of hot regions, dense regions, and long-lived structures. It creates stars where nuclear energy can burn. It creates galaxies where matter can gather. It creates clocks by making time flow unevenly. This is why gravity cannot be reduced to an energetic interaction like the others. It does not exchange energy in the usual sense. It creates the conditions under which exchange becomes meaningful. Once this is understood, the question changes. Instead of asking how gravity stores or transfers energy, we begin to ask what role gravity plays in allowing the universe to evolve at all. Why does structure form? Why does time have a direction? Why does complexity emerge rather than dissolve instantly into equilibrium? Energy alone cannot answer these questions. Energy conservation does not explain why there are gradients to exploit. It does not explain why the universe is not perfectly uniform. It does not explain why time seems to flow forward. Gravity, however, sits at the center of all three. By bending space-time, gravity creates asymmetries. By deepening curvature, it allows matter to clump. By shaping time itself, it gives processes a direction. Energy then flows along the paths gravity makes available. In this light, gravity begins to look less like a participant and more like a rule set. It is not competing with energy. It is defining the space of possibilities within which energy operates. This realization does not solve every mystery, but it sharpens the question we must ask next. If gravity is not fuel and energy is not fundamental, then what truly drives change in the universe? What pushes systems forward? What gives motion and time their apparent urgency? To answer that, we must turn to a concept often misunderstood, often oversimplified, and often blamed for everything from decay to doom. Entropy. Entropy enters the discussion quietly, but once it does, gravity's strange role becomes impossible to ignore. Entropy is often described as disorder, but that word is misleading. Entropy is not chaos. It is probability. It is a measure of how many microscopic arrangements correspond to what we see macroscopically. Systems evolve not because they seek disorder, but because they move towards states that can be realized in more ways. In a universe governed only by energy conservation, entropy would still increase, but nothing especially interesting would happen. Energy would spread out evenly, temperatures would equalize, motion would fade into uniformity. The universe would become smooth, featureless, and dull very quickly. And yet our universe did the opposite. Structure formed, matter clumped, stars ignited, galaxies emerged, complexity grew. This should seem paradoxical. Gravity appears to create order, while entropy is supposed to destroy it. For a long time, this was treated as a contradiction to be explained away. But it is not a contradiction at all. Gravity increases entropy more efficiently than almost any other process in the universe. When matter collapses under gravity, the number of possible microscopic arrangements explodes. A cloud of gas spread thinly through space has relatively few configurations. The same gas compressed into a star has vastly more internal states. Gravity creates localized order, while enabling a much larger increase in total entropy. This is the key. Gravity does not fight entropy, it accelerates it. As matter falls inward, gravitational potential deepens. Energy is released, radiation is emitted, heat flows outward, and entropy increases dramatically. The apparent order of stars and galaxies is paid for by an enormous increase in entropy elsewhere. Gravity is the mechanism that makes this trade possible. Energy alone would never do this. Energy gradients flatten. Gravity creates new gradients as fast as old ones disappear. It continually generates low entropy pockets that allow energy to flow again and again. This is why gravity feels inexhaustible. It is not consuming fuel. It is opening pathways through the space of possible states. It is not doing work in the energetic sense. It is reshaping the probability landscape. Seen this way, gravity begins to look like a driver of evolution, not because it spends energy, but because it creates the conditions under which entropy can grow most efficiently. It carves the universe into regions where time can have direction, where processes can unfold, where complexity can arise temporarily before dissolving again. Energy tells you how fast something happens. Entropy tells you which way it happens. Gravity tells you where it can happen at all. This triad clarifies the hierarchy that has been obscured for so long. Energy is conserved, but conservation does not give direction. Entropy increases, but entropy needs structure to increase through. Gravity supplies that structure by shaping space-time and creating gradients. This is why a universe without gravity would be a universe without meaningful time. Without gravity, there would be no stars to burn, no clocks to tick differently, no collapse to drive irreversible processes. Everything would expand, cool, and equilibrate almost immediately. Time would lose its arrow because nothing would distinguish past from future in a meaningful way. Gravity gives time something to do. It creates long-lived structures that persist far from equilibrium. It allows entropy to increase in stages rather than all at once. It stretches the unfolding of the universe across billions of years instead of moments. In doing so, it gives rise to history. At this point, the original assumption looks increasingly fragile. Energy does not run the universe in the way fuel runs an engine. Energy is a quantity defined within a gravitationally structured space-time. It moves, transforms, and balances, but it does not decide the rules of the game. Gravity decides those rules. It determines how space bends, how time flows, how matter clusters, and how entropy grows. Energy then follows, constrained by the geometry gravity provides. What we experience as cause and effect, motion and rest, past and future, all unfold within that framework. By the end of this chapter, the conclusion becomes difficult to avoid. Gravity does not behave like energy because it is not energy. It is not fuel, not currency, not a resource that can be spent. It is structure. It is rule. It is the silent architecture that makes energy meaningful at all. And once that is accepted, the next step becomes unavoidable. If gravity is geometry, and geometry shapes entropy and time, then perhaps gravity is not fundamental in the way we usually imagine either. Perhaps even gravity itself emerges from something deeper. To explore that possibility, we must follow the idea to its most radical conclusion, the moment when gravity stopped being a force entirely and became something stranger, more subtle, and more profound. Gravity was still imagined as a force in the traditional sense, invisible, long-ranged, and mysterious, but conceptually familiar. Objects pulled on one another across empty space, exchanging influence the way magnets or electric charges do. This picture had worked well enough for centuries, guiding predictions of planetary motion with astonishing accuracy. But it was hiding a deeper truth that only revealed itself when physics pushed beyond the comfortable boundaries of intuition. The turning point came when gravity was stripped of its status as a force entirely. Instead of asking how masses pull on one another, the question was reframed. What if motion itself was being misunderstood? What if objects were not being pushed or pulled at all, but were simply following the natural shape of space-time? This shift was not cosmetic. It overturned the very foundation of how gravity was understood. Space and time, once treated as separate and absolute, were fused into a single structure. That structure could bend, stretch, and curve. And what we experience as gravity was nothing more than the consequence of moving through that curved geometry. Matter and energy influence space-time, telling it how to curve. Space-time, in turn, influences matter and energy, telling them how to move. This relationship is often summarized in a single elegant sentence, but the simplicity is deceptive. Embedded within it is a complete reversal of the traditional hierarchy of explanation. Gravity was no longer something that happened within space and time. It was space and time doing something. Once this idea is taken seriously, the language of energy begins to look increasingly inadequate. Energy can move through space. It can be stored, transferred, and transformed. Space-time cannot. Space-time is not a substance. It is the arena itself. It does not flow. It does not accumulate. It simply defines what motion and change mean. This is why gravity does not run out. Curvature does not decay when objects move along it. A valley does not flatten because a river flows through it. Geometry constrains motion without paying any cost. The motion happens because of the shape, not because something is being spent. This realization dissolves many long-standing puzzles at once. Why does gravity seem inexhaustible? Why does it act without loss? Why does it refuse to be localized as energy? Because it is not something that acts. It is something that is. Energy tells space-time how to curve, but that statement is often misunderstood. It does not mean energy powers curvature the way fuel powers an engine. It means energy is part of the description of how matter and motion relate to geometry. The curvature does not consume energy to exist. It responds to the presence of energy by taking on a particular shape. This distinction matters because it prevents a common misinterpretation. When space-time curves in response to energy, nothing is being spent. There is no energetic transaction. There is only structure adjusting to content. Once curved, space-time simply remains curved unless the distribution of matter and energy changes. It does not leak. It does not fade. It does not demand maintenance. This is why gravitational effects persist long after energetic processes have run their course. A star can burn through its nuclear fuel and collapse, but the curvature it created does not vanish. A black hole, once formed, does not need energy input to continue influencing its surroundings. The geometry remains, defining motion indefinitely. This leads to a startling implication. Gravity does not flow forward in time the way energy does. It does not dissipate into heat. It does not degrade into less useful forms. It is indifferent to the arrow of time. It shapes time itself without being shaped by it in return. Energy degrades. Entropy increases. But curvature remains. This alone suggests that gravity sits at a deeper level than energy. Energy obeys rules that gravity defines. Energy moves through space-time. Gravity is space-time. Once this is accepted, the question of what runs the universe must be reformulated. If gravity is geometry, then the universe is not a machine driven by fuel. It is a structure unfolding according to rules that do not age or weaken. Energy animates processes, but geometry decides what processes are possible. This reframing also explains why attempts to unify gravity with other forces have been so difficult. The other interactions live within space-time. Gravity is space-time. Trying to treat it as just another force is like trying to describe the shape of a chessboard using the rules of the pieces. The radical shift introduced here did more than solve anomalies. It changed the meaning of explanation itself. Instead of asking what causes gravity, physics was forced to ask what causes geometry. Instead of asking how gravity uses energy, it had to ask whether energy is meaningful without gravity at all. At this point, the idea that energy runs the universe begins to look less like a principle and more like a habit of thought. Energy is essential for describing what happens within the universe. But gravity defines the universe in which anything can happen. If gravity is geometry, and geometry is the stage on which energy plays out, then perhaps geometry is the true engine of reality. Not an engine that consumes fuel, but a rule that defines possibility. And if geometry is fundamental, then the next question becomes unavoidable. What determines geometry itself? Why does space-time take the shape it does? Why do the rules exist at all? To approach that question, We must look away from fuel and forces entirely and towards something far more subtle. Gradients. Once gravity is understood as geometry, the idea of forces pushing things around begins to fade into the background. What remains is something quieter but more powerful. Differences, slopes, gradients woven into the fabric of space-time itself. Motion, in this view, is not driven by fuel. It is guided by imbalance. Things move because the geometry they inhabit is uneven. This is a profound shift. In everyday thinking, we imagine motion as something that must be caused actively, a push, a pull, an expenditure. But in a geometric universe, motion is often the default. Objects follow the paths that are already available to them. They move not because energy demands it, but because curvature allows it. Consider how light travels near a massive object. Light has no rest mass. It does not slow down or speed up in the usual sense, and yet its path bends. The bending is not the result of a force acting on light or energy being transferred to it. The bending occurs because the geometry of space-time is curved. The straightest possible path is no longer what our intuition expects. Nothing is spent in this process. No energy is drained from the gravitational field. The path simply exists and light follows it. The same is true for matter. Planets orbit stars not because they are constantly pulled inward by a force that consumes something, but because space-time around the star is shaped in a way that makes circular paths natural. Remove the curvature and the motion disappears. Leave the curvature and the motion persists indefinitely. This reveals something deeply unintuitive. Stability does not require energy input. It requires geometry. Once this is seen, the language of engines and fuel begins to feel misplaced. Engines consume resources to maintain motion against resistance. But in space-time, resistance is not fundamental. Geometry replaces friction. Paths replace pushes. This also explains why gravity dominates on large scales, even though it is incredibly weak on small ones. Gravity does not need to overpower other forces. It only needs to shape the overall geometry. Once geometry is set, everything else must comply. Strong forces may bind nuclei, electromagnetism may govern chemistry, but gravity decides where matter can gather and how time flows around it. Energy is powerful locally, geometry is powerful globally. This perspective resolves a long-standing puzzle. Why does gravity control the large-scale structure of the universe, even though it is the weakest interaction? Because strength is the wrong metric. Geometry does not compete, it constrains. It does not push harder. It defines the paths along which pushing makes sense. Seen this way, the universe is not driven forward by an energetic motor. It is unfolding along gradients that are built into space-time itself. Curvature gradients guide motion. Time gradients shape clocks. Density gradients shape collapse and expansion. Energy flows down these gradients, but it does not create them. This inversion helps clarify why energy conservation remains so powerful without being fundamental. Conservation laws emerge from symmetry. In a space-time that is uniform in time, energy is conserved. In a space-time that is uniform in space, momentum is conserved. These are not arbitrary rules. They are consequences of geometry. Change the geometry and the rules change. In an expanding universe, time symmetry is broken globally. Energy conservation becomes ambiguous. Photons lose energy as space stretches, not because they give it to something else, but because the definition of energy itself depends on the structure of space-time. Geometry changes, and energy bookkeeping adjusts accordingly. Gravity is not violating conservation laws. It is defining when and where they apply. This realization strips energy of its assumed sovereignty. Energy is no longer the ruler of reality. It is a citizen living under laws set by geometry. Useful, measurable, indispensable, but not in charge. At this stage, a deeper pattern begins to emerge. Everywhere we look, what drives motion and change is not the presence of energy, but the presence of gradients. Differences in curvature, differences in density, differences in time flow. Where gradients exist, things happen. Where gradients vanish, nothing changes. This suggests that the true engine of the universe may not be energy at all, but the existence of unevenness in space-time itself. Geometry creates the slopes, energy rolls down them, and that realization sets up the next step in the argument. If gravity is geometry, and geometry creates gradients, then perhaps the universe does not run on fuel, but on imbalance. Perhaps change itself is a response to structure, not expenditure. To see where this leads, we must step back and ask a deceptively simple question. What happens in a universe with no gradients at all? Imagine a universe with no gradients, no differences in curvature, no differences in density, no differences in time flow. Everything perfectly uniform, everywhere the same, at every moment. In such a universe, energy could exist, but nothing would happen. Motion would have no preferred direction. Processes would have no reason to begin or end. Time would lose its meaning because nothing would distinguish one moment from the next. This thought experiment reveals something crucial. Energy by itself does not create change. Energy requires gradients to matter. Without unevenness, energy becomes inert, a quantity with no consequence. It is gravity that prevents the universe from becoming this featureless stillness. By curving space-time unevenly, gravity ensures that gradients exist everywhere. Time flows at different rates. Space stretches differently in different regions. Matter experiences slopes in the geometry that guide its motion. These differences are what allow processes to unfold. This reframes the arrow of time in a profound way. We often say time flows forward because entropy increases, but entropy increases because systems move along gradients toward more probable states, and those gradients exist because space-time is not uniform. Gravity is what breaks the symmetry. Without gravity, entropy would still be defined, but it would reach its maximum almost instantly. There would be no long-lived structures to delay equilibrium. No stars, no galaxies, no slow unfolding of complexity. Time would exist mathematically, but it would have no narrative. Gravity gives the universe a story. It stretches the journey toward equilibrium across billions of years. It creates pockets where entropy can grow slowly, step by step, rather than all at once. In doing so, it allows cause and effect to matter. It allows history to exist. This is why geometry feels deeper than energy. Energy tracks what happens along the way. Geometry determines whether there is a way at all. At this point, the hierarchy becomes hard to deny. Energy describes motion. Entropy gives motion direction. Gravity creates the gradients that allow both to exist. Remove gravity, and energy loses relevance. Remove energy, and geometry still defines paths. This does not mean gravity acts alone. It means gravity sets the stage on which all other actors perform. The universe is not burning fuel to keep going. It is unfolding according to rules embedded in space-time itself. Once this is accepted, the question shifts again. If gravity is geometry, and geometry creates gradients, then where does geometry come from? Is space-time fundamental, or does it emerge from something even deeper? Some of the most radical ideas in modern physics suggest that gravity itself may not be fundamental, that it may arise from thermodynamics, information, or quantum structure. In these views, gravity is not the base of reality, but a large-scale expression of something more primitive. And if gravity can emerge without being powered by energy, then the idea that the universe runs on energy becomes even more fragile. To explore that possibility, we must follow gravity beyond geometry and into the realm where space-time itself begins to dissolve, where entropy, information, and reality blur together. Is deeply intuitive. We live in a world of engines, fires, and consumption. Cars move because fuel burns. Bodies function because chemical energy is spent. Stars shine because nuclear fuel is exhausted over time. Everywhere we look locally, Motion is tied to expenditure. It feels natural to extend that intuition to the cosmos itself. But intuition, shaped by everyday experience, can be dangerously misleading when applied to the universe as a whole. On the largest scales, nothing behaves like an engine. Galaxies do not burn fuel to rotate. Planetary systems do not consume resources to remain stable. Space-time itself does not age, corrode, or weaken through use. What we observe instead is something quieter and far more persistent. Motion follows differences. Change follows imbalance. Evolution follows gradients. A gradient is simply a difference across space or time. A difference in temperature, a difference in pressure, a difference in density, a difference in curvature. Wherever a gradient exists, motion follows naturally. Heat flows from hot to cold. Matter moves from dense to sparse. Light bends toward regions of deeper curvature. Time itself flows at different rates depending on gravitational environment. Nothing needs to be spent for this to happen. The gradient already exists. Motion is the response. This is the crucial inversion. Motion does not require fuel. Motion requires a slope. In everyday life, we confuse the two because gradients are often created by burning fuel. A fire creates a temperature gradient. A battery creates an electric potential difference. An engine maintains a pressure gradient. But these are local tricks, artificial ways of sustaining imbalance against a broader tendency toward equilibrium. The universe does not need such tricks. Gravity creates gradients naturally, continuously, and without cost. By curving space-time unevenly, gravity ensures that differences exist everywhere. These differences are what allow anything to happen at all. Consider again something as simple as a falling object. We say it falls because gravitational potential energy is converted into kinetic energy. But this language hides the deeper mechanism. The object falls because space-time is curved in such a way that the straightest possible path leads downward. The gradient exists before the motion. Energy bookkeeping describes the motion after the fact. The same logic applies to orbits, to collapsing gas clouds, to light bending near massive objects. In every case, geometry creates a slope. Matter and radiation follow it. Energy tracks the process, but does not initiate it. This distinction becomes even more important when we think about time. Time does not flow uniformly across the universe. Clocks closer to massive objects tick more slowly than clocks farther away. This difference is not caused by energy being drained from the clock. It is caused by a gradient in space-time itself. Gravity creates a slope. In time, processes unfold along that slope. Cause precedes effect because the geometry enforces it. Without gravitational time gradients, the arrow of time would be far less meaningful. What we call dynamics is therefore not powered by energy in the way engines are powered. It is guided by gradients embedded in space-time. Energy moves downhill in probability space. Matter moves downhill in curvature. Radiation moves along paths shaped by geometry. Fuel is consumed. Gradients are followed. This explains a puzzle that has lingered quietly beneath modern cosmology. Why does the universe continue to evolve even as usable energy decreases? Why does structure continue to form even as energy differences flatten? The answer is that gravity keeps creating new gradients faster than energy can erase them. As matter clumps, curvature deepens. As curvature deepens, new paths open. As new paths open, new processes unfold. Energy degrades. Gradients regenerate. This is why the universe does not behave like a machine winding down. Machines depend on stored energy. When the energy is gone, motion stops. The universe depends on structure. As long as space-time remains uneven, motion continues. Seen this way, gravity is not competing with energy. It is operating at a deeper level. Energy tells you how fast something happens. Gravity tells you where it can happen. Entropy tells you which direction it will go. This triad reveals the true hierarchy. Energy is descriptive, entropy is directional, gravity is generative. And once this is understood, the question of what runs the universe becomes clearer. The universe does not run on fuel. It runs on difference, on imbalance, on gradients carved into space-time itself. To understand why this matters even more deeply, we must now follow gradients to their ultimate consequence, the tendency of systems to move toward what is most probable, the principle that gives time its arrow and motion its inevitability. Entropy. Once gradients are recognized as the true drivers of change, many familiar ideas begin to reorganize themselves. Energy no longer sits at the center of the story. It becomes a secondary quantity, a way of describing how systems move once differences already exist. The real question shifts from how much energy is available to how uneven the universe is allowed to be. Every physical process we observe can be traced back to a gradient. Heat flows because there is a temperature difference. Wind blows because there is a pressure difference. Rivers flow because there is a height difference. Even chemical reactions proceed because there is a difference in potential between molecular states. Remove the difference, and the process halts, no matter how much energy is present. Gravity is unique because it does not merely respond to gradients, it creates them. By curving space-time, gravity generates differences in distance, time, and probability itself. It creates regions where clocks tick slowly and regions where they tick quickly. It creates basins where matter naturally accumulates and ridges that matter avoids. These are not energetic effects in the usual sense. They are structural features of reality. Once created, these features persist. They do not need maintenance. They do not require replenishment. A curved space-time remains curved unless the distribution of matter changes. Motion continues because the slope remains. This is why gravitational systems can remain active for extraordinarily long times. A planetary orbit can persist for billions of years without energy input. A galaxy can rotate long after its brightest stars have burned out. A black hole can influence its surroundings long after the violent events that formed it have faded into the past. The activity does not come from fuel. It comes from form. This realization also explains why attempts to model the universe as a thermodynamic engine eventually run into trouble. Engines require a hot reservoir and a cold reservoir. They extract work by exploiting a temperature gradient. But the universe does not sit between two reservoirs. It is the entire system. There is no outside source feeding it energy. And yet change continues. The reason is that gravity continually reshapes the internal landscape. As matter clumps, new gradients appear. As stars form, radiation escapes into space, increasing entropy while deepening gravitational wells. The universe creates its own slopes and then slides down them. Energy participates in this process, but it does not initiate it. Energy follows the paths gravity provides. It converts, disperses, and degrades along the way, but the underlying structure remains. This is why energy alone cannot explain cosmic evolution. If energy were the sole driver, the universe would have smoothed itself out rapidly and remained in a dull equilibrium state ever since. The persistence of structure demands something that resists flattening. Gravity provides exactly that. Even cosmic expansion fits into this picture. As space stretches, energy densities dilute. Photons lose energy as their wavelengths stretch. But the expansion itself is not powered by that energy loss. It is a geometric process. Space expands because the geometry evolves, not because energy is pushing it outward. Again and again, the same pattern appears. Geometry first, energy second. This does not mean energy is irrelevant. It means energy is responsive. It reacts to gradients. It does not create them. When physicists say energy drives change, they are often describing what happens locally, not what determines the global structure. On the larger scales, the universe behaves less like an engine and more like a landscape. Hills and valleys exist. Matter and radiation move through them. The movement does not exhaust the landscape, it reveals it. Once this is understood, the phrase energy runs the universe begins to sound like a metaphor that has been taken too literally. Energy describes motion within the universe. It does not explain why motion is possible in the first place. That explanation lies in the existence of gradients, and gradients arise from gravity. But gradients alone are not the full story. They explain why motion occurs, but not why it occurs in a particular direction. For that, we must return to entropy, not as disorder, but as probability, not as decay, but as inevitability, because gradients tell systems where they can go. Entropy tells them where they will go. Entropy is often treated as an afterthought, a kind of bookkeeping rule that explains why things fall apart. But in the context of gradients and gravity, entropy becomes something far more central. It is the principle that turns structure into motion and imbalance into history. Entropy does not create gradients, but it ensures they are used. At its core, entropy measures how many microscopic ways a system can be arranged while still appearing the same at a large scale. A state with high entropy is not messy in a casual sense. It is simply more probable. There are more ways for it to exist. Systems move toward these states not because they prefer disorder, but because probability overwhelms every other consideration. In a perfectly uniform universe, entropy would already be maximized. Nothing would change because nothing could change. Every configuration would be equivalent. Time would pass, but nothing would mark its passage. Gravity prevents this fate. By creating gradients, gravity pushes the universe far from equilibrium. Matter clumps. Time slows in some regions and speeds up in others. Energy becomes unevenly distributed. These differences create opportunities for entropy to grow in stages rather than all at once. This is why gravity is essential to the arrow of time. Entropy increases because systems explore more probable states, but those states are made available by the structure of space-time itself. Gravity opens doors in the space of possibilities. Entropy walks through them. Stars are a perfect example. A diffuse cloud of gas has relatively few ways to arrange itself. When gravity pulls that gas together into a star, the number of possible internal configurations increases dramatically. Heat is generated. Radiation escapes. Entropy skyrockets. The star looks ordered from a distance, but the universe as a whole becomes far more probable. Energy flows outward. Structure forms inward. Entropy grows everywhere. This process repeats on every scale. Galaxies form from collapse. Black holes form from extreme collapse. Each step creates apparent order locally, while driving an even greater increase in entropy globally. Gravity is not fighting entropy, it is enabling it. This is why the universe looks structured, even as it moves relentlessly toward equilibrium. Gravity keeps creating new gradients faster than entropy can erase them. It delays the end state not by resisting probability, but by amplifying it. Seen this way, gravity is not merely compatible with entropy, it is entropy's greatest ally. Energy plays a supporting role. Energy moves along the gradients gravity creates and entropy favors. It heats, radiates, disperses, and transforms. But it does not choose direction. It does not choose outcome. Those choices are dictated by geometry and probability. This reframing dissolves the last remaining justification for treating energy as the engine of reality. Engines impose direction. Energy does not. Entropy does. Engines require fuel. Gravity does not. The universe evolves because it is allowed to be uneven, and because unevenness makes some states overwhelmingly more likely than others. Gravity ensures unevenness persists. Entropy ensures it is used. Energy simply keeps score. Once this is understood, the phrase "energy runs" the universe loses its meaning. The universe is not being powered forward. It is relaxing into what is allowed, guided by geometry and probability. This perspective sets the stage for a deeper and more unsettling possibility. If gravity creates gradients and entropy exploits them, then perhaps gravity itself is not fundamental either. Perhaps it emerges from even deeper principles related to information, statistics, or thermodynamics. If that is true, then energy is not just secondary. It is several layers removed from the foundation of reality. To explore that possibility, we must step into one of the most radical ideas in modern theoretical physics: the suggestion that gravity itself may emerge not from force or geometry, but from entropy. It is blamed for decay, for aging, for the inevitable breakdown of structure. In popular explanations, entropy is disorder, the reason things fall apart, the cosmic tax that must always be paid. But this framing hides its true role. Entropy is not destruction, it is selection. It is the quiet rule that decides which states of the universe are likely and which are almost impossible. At its heart, entropy is a measure of possibility. It counts how many microscopic arrangements correspond to what we observe at large scales. A high entropy state is not chaotic by necessity, it is simply common. There are many ways for it to exist. A low entropy state is rare, not because it is forbidden, but because it is unlikely. The universe does not move toward entropy because it wants to decay. It moves because probability overwhelms resistance. Systems evolve towards states that can be realized in more ways. Time has a direction because probability does. But probability alone is not enough. Without structure, probability would have nothing to act on. Entropy requires pathways. It requires a landscape of possibilities through which systems can move. Gravity provides that landscape. This is the missing connection. Gravity creates low entropy configurations by pulling matter together. A smooth, diffuse universe has relatively few ways to be arranged. When gravity causes matter to clump, the number of internal configurations increases dramatically. Temperatures rise, radiation escapes, entropy surges. The appearance of order is deceptive. The universe becomes vastly more probable overall. This is why stars can exist at all. A star is not a violation of entropy. It is an entropy engine. It forms because gravity creates a low entropy structure that allows an even larger increase in entropy elsewhere. The star shines, energy radiates outward, space fills with heat. The universe moves toward higher probability. Energy alone could never accomplish this. Energy tends to spread. Left to itself, it erases gradients. Gravity does the opposite. It concentrates matter, deepens curvature, and creates new opportunities for entropy to grow. This partnership explains why motion persists, even as energy differences flatten. Entropy wants systems to explore more probable states. Gravity keeps creating new routes through probability space. Energy simply follows along, converting, dispersing, and keeping track. Once this is seen, motion itself takes on a different meaning. Objects do not move because energy pushes them forward. They move because there are overwhelmingly more ways for them to be in one state than another, given the structure of space-time. Motion is the visible trace of probability flowing downhill. Time's arrow emerges naturally from this picture. The past is the set of rare states. The future is the set of common ones. Gravity ensures that the universe starts in an extremely special, low-entropy configuration. Entropy ensures it does not stay there. This also explains why time feels irreversible. You can scramble an egg but never unscramble it, not because it violates energy conservation, but because the scrambled state has astronomically more possible arrangements. The universe does not remember how to go backward because backward is vanishingly unlikely. Gravity plays a crucial role in stretching this process out. Without gravity, entropy would reach its maximum almost immediately. There would be no long-lived structures, no gradual evolution, no extended history. Gravity delays equilibrium by constantly reshaping the space of possibilities. In doing so, gravity gives entropy room to act slowly. It turns a rapid collapse into a long story. It allows complexity to arise temporarily before probability claims it again. Energy participates in all of this, but it does not drive it. Energy moves through the channels gravity carves and entropy favors. It does not choose the channels. It does not choose the direction. It is carried along by deeper rules. This is why energy feels insufficient as an explanation for motion. Energy explains how much work can be done. Entropy explains which processes will occur. Gravity explains why there are processes at all. Once this hierarchy is recognized, the universe no longer looks like a machine running on fuel. It looks like a probability landscape unfolding according to structure. Motion is not powered, it is permitted, and that realization opens the door to an even more radical idea. If entropy and probability are so central, then perhaps gravity itself is not fundamental geometry, but an emergent phenomenon arising from statistical behavior at a deeper level. This is not speculation without foundation. It is a line of thought that has already begun to reshape theoretical physics. If gravity and entropy are this tightly linked, then the familiar picture of gravity as a fundamental force begins to feel incomplete. Forces usually exchange something: momentum, energy, information. Gravity, however, seems to orchestrate outcomes without trading in any obvious currency. It shapes probability rather than pushing matter directly. This odd behavior has led some physicists to ask a question that would once have sounded heretical. What if gravity is not fundamental at all? In this view, gravity would not be the source of structure, but the visible consequence of deeper statistical behavior. Just as temperature emerges from the collective motion of particles, gravity might emerge from the collective behavior of microscopic degrees of freedom that are not themselves geometric. Space-time curvature would then be a large-scale effect, not a primitive ingredient. This idea sounds radical, but it fits remarkably well with what we have already seen. Gravity creates gradients that entropy exploits. But entropy itself is a statistical concept. It does not belong to individual particles. It belongs to ensembles. It arises when many degrees of freedom are coarse-grained into a simpler description. If gravity behaves like an entropic phenomenon, then its refusal to act like energy makes sense. An entropic force does not exist as a fundamental interaction. It arises because systems move toward more probable states. The classic example is a stretched polymer molecule. When released, it contracts, not because there is a microscopic force pulling it inward, but because there are vastly more microscopic configurations corresponding to the contracted state. The apparent force is statistical. If gravity is similar, then objects fall not because space-time commands them to, but because there are more microscopic states corresponding to their being closer together, given the underlying information structure of the universe. The curvature we describe mathematically would then be a macroscopic summary of deeper probabilistic behavior. This would explain why gravity feels geometric rather than energetic. Geometry would be the language we use to describe the collective behavior of underlying information. Energy would remain a useful quantity for tracking motion, but it would not be responsible for the attraction itself. In this picture, entropy does not merely follow gravity, it generates it. As systems evolve toward more probable configurations, the effective geometry they experience changes. What we interpret as gravitational attraction would be the tendency of information to rearrange itself in ways that maximize entropy. Space-time curvature would be the emergent bookkeeping tool we use to describe that rearrangement at large scales. This perspective also explains why gravity is universal. Every form of energy and matter participates in it. Entropic effects are universal because they arise from counting possibilities, not from specific interactions. Anything that contributes to the underlying information content contributes to gravity. Energy then becomes even more clearly secondary. Energy measures the ability to cause change within a given structure. Entropy determines which changes are favored. Gravity would emerge from that favoritism itself. Seen this way, the universe does not move because energy is being spent. It moves because probability is being maximized. Geometry adjusts to reflect that motion. Energy tracks it. Entropy drives it. This is a dramatic inversion of the traditional narrative. Instead of energy creating motion and gravity responding, probability creates structure and energy responds. The universe is not powered forward. It is statistically compelled. If this is correct, then the deepest engine of reality is not energy at all. It is information, the arrangement of degrees of freedom, the counting of possibilities. Gravity would be the large-scale shadow cast by that counting. This idea is still incomplete and deeply debated, but it has already reshaped how physicists think about space, time, and causation. It suggests that what we experience as force and motion may be emergent stories told by much deeper rules. And if gravity emerges from entropy, then the arrow of time, the flow of motion, and the structure of the universe are all tied together at a level far beneath energy conservation. To see how far this idea can be taken, we must now confront a question that lies at the heart of experience itself. Does gravity merely shape motion in time, or does it help create time's direction in the first place? Entropy does more than guide motion. It gives time its meaning. Without entropy, time would be a parameter with no direction, a label with no story attached. Events could be ordered, but nothing would distinguish before from after in a physically meaningful way. Entropy turns time into a narrative by making some transitions overwhelmingly more likely than others. Gravity plays a central role in this transformation. By creating low-entropy structures, gravity ensures that the universe begins in an extraordinarily special state. A smooth, early universe is not a state of high entropy, as intuition might suggest. It is a rare configuration, one with very few possible arrangements compared to the clumped, structured universe that follows. Gravity takes that rarity and amplifies it into history. As matter collapses, stars form, galaxies assemble, and black holes emerge, the number of accessible microscopic states increases enormously. Entropy rises, but it rises along paths carved by gravity. Time gains direction, not because energy is being used up, but because probability is being explored. This is why the arrow of time points the same way everywhere we look. It is not imposed by a fundamental law that demands time flow forward. It emerges because the universe started in a low-entropy configuration shaped by gravity, and there are vastly more ways to go forward than backward from that starting point. Energy conservation alone cannot explain this. Energy conservation is symmetric in time. The equations work just as well backward as forward. Entropy breaks that symmetry. Gravity sets the stage on which the symmetry is broken. This connection becomes even clearer when we consider what would happen in a universe without gravity. Without gravity, matter would never clump. There would be no stars, no galaxies, no long-lived structures. Entropy would reach its maximum almost immediately. Time would still exist mathematically, but it would have no arrow. Nothing would meaningfully change. Gravity slows the rush to equilibrium. It stretches entropy increase across cosmic time. It allows the universe to explore probability space gradually rather than instantly. In doing so, it creates the conditions for complexity, memory, and cause and effect. This makes gravity deeply entangled with time itself. Gravity does not merely act within time. It helps define why time has direction. It creates situations where the future is statistically distinct from the past. Energy participates in this unfolding, but it does not decide the direction. Energy can flow backward just as easily as forward in the equations. Entropy and gravity together decide which flows actually occur. At this point, the hierarchy becomes unmistakable. Energy describes what happens locally. Entropy explains why it happens in one direction rather than another. Gravity ensures there is a long-lived path between rare beginnings and common endings. This is why the idea that energy runs the universe feels increasingly inadequate. Engines consume fuel and eventually stop. The universe does not behave that way. It evolves because probability is being explored within a structure that does not wear out. Gravity is not fuel. Entropy is not fuel. They are not consumed. They are rules. Energy, by contrast, behaves like fuel because it is defined within those rules. It flows, degrades, and disperses, but it does so because geometry and probability allow and encourage it. Once this is understood, the original question can finally be reframed properly. The universe does not run on energy in the way a machine runs on gasoline. It unfolds according to structure and statistics. Energy is the language we use to describe the motion that results. Gravity creates the landscape. Entropy chooses the direction. Energy traces the path. This perspective does not diminish the power of energy conservation. It explains it. Conservation laws arise because of symmetries in space-time. They are consequences, not causes. Change the structure, and the bookkeeping rules change with it. With this realization, we stand at the edge of a deeper synthesis. If gravity may emerge from entropy, and entropy gives time direction, then perhaps gravity is not only shaping motion, but shaping time itself. To explore that idea, we must now confront one of the most subtle questions in physics. Does gravity merely influence clocks, or does it help create the flow of time? Sounds radical only because of how familiar gravity feels. It shapes every experience, from the weight of our bodies to the motion of galaxies. Yet familiarity has misled physics before. Heat once felt fundamental. Temperature once felt like a substance. Both turned out to be emergent descriptions of deeper behavior. Gravity may be undergoing the same quiet demotion. The first serious cracks in gravity's fundamental status appeared when physicists noticed something unsettling. The equations describing gravity could be derived without ever assuming gravity existed in the first place. Instead, they could be reconstructed from thermodynamics, statistics, and information. Geometry appeared not as a starting point, but as an outcome. This shift began with the realization that space-time behaves like a thermodynamic system. Horizons have temperatures. Black holes have entropy. Area, not volume, determines information content. These facts are not decorative curiosities. They point toward a deep connection between gravity and statistical behavior. If space-time has entropy, then it must be composed of microscopic degrees of freedom. Entropy counts possibilities. Something must be doing the counting. Geometry, once assumed continuous and fundamental, begins to look like an effective description of something discrete underneath. In this view, gravity is not a force, and not even truly geometry. It is the large-scale behavior of underlying information rearranging itself toward more probable configurations. Space-time curvature becomes the macroscopic signature of that rearrangement. This explains several mysteries at once. Why gravity is universal. Why it couples to everything with energy and momentum. Why it resists localization as energy. Why it behaves more like a rule than a resource. These are exactly the properties one would expect from an emergent phenomenon. An emergent force does not carry its own fuel. It does not require expenditure. It arises because the system as a whole prefers certain configurations over others. Objects fall not because something pulls them, but because there are more microscopic ways for them to be lower rather than higher in the gravitational landscape defined by information. This perspective also clarifies why energy seems insufficient as a foundation. Energy is a useful quantity only once degrees of freedom and time already exist. Entropy, by contrast, counts possibilities independent of how we label motion. Information comes first. Geometry follows. Energy is defined last. When viewed this way, the universe does not begin with energy and then build structure. It begins with structure in the informational sense. Energy emerges as a way of tracking change within that structure. This inversion feels uncomfortable because it reverses centuries of habit. We are used to explaining motion by appealing to forces and fuels. But emergence teaches a different lesson. The deepest laws are not about pushing, they are about counting. Gravity then becomes the statistical tendency of information to organize itself in a way that maximizes entropy, subject to constraints. Curvature is not imposed, it appears. Time does not flow because energy is spent. It flows because probability is explored. This view does not eliminate gravity, it deepens it. Gravity becomes the visible expression of invisible bookkeeping, happening at a level beneath space-time itself. At this stage, energy's role becomes clear. Energy is not the engine of reality. It is the currency used by subsystems once reality already has structure. It moves things around, but it does not decide the rules of motion. Those rules arise from deeper statistical principles. The universe, then, is not powered. It is organized. And if gravity emerges from information and entropy rather than energy, then one final question becomes unavoidable. If gravity shapes space-time and space-time shapes time, then is time itself emergent from gravity? If gravity emerges from information and entropy, then time itself can no longer be treated as a primitive backdrop. Time becomes something that arises alongside gravity, shaped by the same statistical logic. This possibility changes the meaning of duration, sequence, and even causation. In ordinary thinking, time is assumed to exist first. Events happen within it. Energy moves through it. Gravity acts across it. But emergent gravity suggests a different order. Information rearranges. Entropy increases. Geometry appears. And time emerges as a measure of that rearrangement. In this picture, time is not a river flowing independently of the landscape. It is the bookkeeping of change itself. Where nothing changes, time has no operational meaning. Where entropy grows, time gains direction. Gravity plays a crucial role here because it determines how entropy can grow. By creating horizons, boundaries, and gradients, gravity defines which changes are accessible and which are forbidden. A horizon hides information. Hidden information increases entropy. Increased entropy gives time a direction. This is why black holes are so central to modern thinking about gravity and time. A black hole is not just an object, it is a limit on knowledge. Information that crosses the horizon becomes inaccessible to the outside universe. Entropy increases not because energy is dissipated, but because information is lost from view. Time outside the black hole continues. Time inside follows a different fate. Geometry dictates which histories are possible. Energy becomes secondary, a participant rather than a driver. This connection between horizons and time is not limited to black holes. Any gravitational horizon carries entropy and temperature. Even an accelerating observer in empty space perceives a horizon and a temperature. This suggests that time, entropy, and gravity are inseparable at a deep level. Energy alone cannot explain this. Energy does not know about horizons. Energy does not care about information access. Entropy does. Gravity creates the conditions under which entropy becomes meaningful. Time emerges from that meaning. This reframes the familiar experience of time passing. Time feels real because change is irreversible. Irreversibility arises because probability overwhelmingly favors certain transitions. Gravity ensures that the universe has a low entropy beginning and many high entropy futures. Time flows because there is somewhere to flow toward. Without gravity, this structure collapses. Entropy would saturate almost instantly. There would be no extended sequence of increasingly probable states. Time would exist as a parameter, but it would have no arrow and no story. Energy could still be conserved in such a universe, but conservation would be trivial. Nothing interesting would happen. No memory could form. No history could unfold. This highlights the deepest flaw in the idea that energy runs the universe. Energy conservation does not guarantee evolution. It does not guarantee direction. It does not guarantee complexity. Gravity and entropy do. Emergent gravity ties these threads together. Geometry is not imposed from above. It arises from information organizing itself. Entropy increases because that organization has more ways to exist. Time flows because that increase defines before and after. Energy then appears as a derived concept. It is how subsystems track change once time and geometry are already in place. Energy is powerful within the rules. It is not the source of the rules. This perspective unifies many puzzles that once seemed unrelated. Why gravity resists quantization? Why gravitational energy cannot be localized? Why time has an arrow? Why black holes dominate entropy? All of these point toward gravity not as fuel, but as structure. By the end of this chapter, the conclusion grows unavoidable. The universe does not run on energy. Energy moves things. Entropy gives direction. Gravity creates the stage on which both can exist. And if gravity helps give rise to time itself, then the next question becomes the most unsettling of all. What happens if energy stops flowing but gravity remains? Consider a universe in which energy flow is frozen. No heat transfer, no radiation escaping stars, no chemical reactions progressing. Every local energetic process paused as if time itself were holding its breath. At first glance, such a universe sounds dead, but geometry would still exist. Space-time would still be curved, paths would still be defined, and motion, in a deeper sense, would not vanish. Even without energy transfer, objects would still follow the structure of space-time. World lines would still exist. Causal relationships would still be defined. The geometry would continue to tell matter and light where they are allowed to go, even if nothing is actively exchanging energy. This thought experiment exposes something crucial. Energy flow is not identical to structure. Stopping one does not erase the other. This is the clearest demonstration yet that gravity does not depend on energy in the way engines depend on fuel. Geometry does not require maintenance. It does not consume resources. Once established, it defines possibility independently of energetic activity. In such a frozen energy universe, entropy would also be frozen locally, but not erased conceptually. The probability landscape would still exist. The distinction between more likely and less likely states would remain meaningful, even if transitions between them were halted. Time would become subtle, but not meaningless. Ordering would still exist, even if change slowed to nothing. This reveals a deep separation between energy and the rules that govern reality. Energy animates processes. Gravity defines what processes are possible. Entropy defines which processes are favored. Remove energy flow, and the play pauses. Remove gravity, and there is no stage at all. This hierarchy clarifies why gravity has proven so resistant to being treated like the other interactions. It does not trade in energy. It trades in possibility. It defines constraints rather than transactions. Emergent gravity theories do not weaken this conclusion. They strengthen it. If gravity arises from information and entropy, then it is even further removed from the idea of fuel. Information does not burn. Entropy does not get used up. Probability does not decay. These are structural features, not consumable resources. Energy, by contrast, is always local. It always belongs to processes rather than to the rules governing them. It is powerful, but it is not foundational. It cannot explain why the universe has long-lived structure. It cannot explain why time has direction. It cannot explain why gravity persists without loss. By the end of this chapter, the picture has fully inverted. Energy is no longer the engine of reality. It is a secondary description that becomes meaningful only after geometry, entropy, and time are already in place. Gravity is not powered by energy. It is the framework that makes energy possible. This realization does not diminish the importance of energy. It places it where it belongs. Energy moves things within the universe. Gravity defines what the universe is allowed to be. With this understanding, the final barrier falls. If gravity helps give rise to time, and if time gives rise to energy descriptions, then the deepest question is no longer about fuel or force. It is about whether gravity itself is responsible for the existence of time's arrow. It is easy to forget how strange it really is. We experience it as a steady flow, always forward, never backward. We remember the past, we anticipate the future. Causes precede effects. Nothing in everyday life suggests that time could be optional, emergent, or dependent on anything else. And yet, when examined closely, time turns out to be one of the most fragile concepts in all of physics. The laws governing motion, energy, and forces do not care about direction. They work just as well if time runs forward as if it runs backward. A collision reversed frame by frame obeys the same equations. Energy conservation does not distinguish past from future. Momentum does not prefer one direction of time over another. At the deepest mechanical level, time symmetry reigns. And yet our universe is not symmetric in time. Something breaks that symmetry, and when it breaks, time acquires an arrow. That arrow is not written into the equations of motion. It emerges from how the universe is structured. It emerges from entropy. But entropy alone is not enough. Entropy explains why time has a direction once there is a gradient to follow. It does not explain why such gradients exist on cosmic scales, or why they persist for billions of years. That responsibility falls to gravity. Gravity is the reason the universe did not begin in equilibrium. A smooth early universe might look simple, but from a gravitational perspective, it is extraordinarily special. Matter evenly spread through space represents a low entropy state for a gravitational system. There are vastly more ways for matter to be clumped than smooth. Gravity takes that smooth beginning and turns it into a long, irreversible cascade of structure formation. As matter collapses, entropy increases. As entropy increases, time gains direction. The future becomes the set of more probable states. The past becomes the set of rare ones. Gravity stretches this process across cosmic history, allowing time to feel extended rather than instantaneous. This means time's arrow is not powered by energy consumption. It is shaped by gravitational structure. Energy degrades, but degradation alone does not create time. Entropy creates time's direction. Gravity makes entropy growth slow enough to matter. This connection becomes impossible to ignore when we examine clocks. A clock is not merely a device that measures time. It is a physical system whose operation depends on processes unfolding irreversibly. Clocks rely on entropy gradients, and those gradients are shaped by gravity. Place two identical clocks at different gravitational depths, and they tick at different rates. This is not because one clock has less energy than the other. It is because time itself flows differently where space-time is curved differently. Gravity does not merely influence clocks, it defines what their ticking means. In regions of stronger gravity, time slows. In regions of weaker gravity, time speeds up. This is not a dynamical effect driven by energy flow. It is a geometric effect. The structure of space-time determines the rate at which processes unfold. This alone suggests that time is not independent of gravity. It is entangled with it. If gravity vanished, space-time would flatten. Time would become uniform everywhere. Entropy would saturate almost immediately. There would be no long-lived gradients to distinguish one moment from the next. Time would exist mathematically, but it would lose its arrow and its narrative. Energy could still exist in such a universe. It could still be conserved, but nothing meaningful would happen. Without gravity, there would be no reason for time to feel like a flow rather than a static dimension. This reveals a startling possibility. Gravity may not merely influence time. It may be the reason time behaves the way it does at all. In this view, time is not the stage on which gravity acts. Gravity is the mechanism that gives time structure. It creates regions where change happens slowly and regions where it happens quickly. It creates horizons that divide what can be known from what cannot. It creates asymmetries that entropy exploits. Energy then becomes a tool used by subsystems within time. Energy flows describe how processes unfold once time and geometry already exist. Energy does not create time's arrow, it follows it. This perspective flips the deepest intuition we have about reality. We tend to think time exists first, then energy flows through it, and gravity acts within it. But the evidence points the other way. Gravity shapes space-time. Space-time shapes time. Time allows energy to be defined. Energy is downstream. If this is true, then the universe does not run on energy, and it does not even run on time. It unfolds according to structural and statistical principles that give rise to both. Gravity is not fuel. It is not an engine. It is not even a force in the traditional sense. It is the rule that determines how time, entropy, and energy relate to one another. And if gravity is responsible for time's arrow, then the most extreme gravitational objects in the universe should reveal this truth most clearly. They do. To see why, we must follow gravity to its limit, to the place where energy becomes almost irrelevant and geometry dominates everything. Black holes. Black holes sit at the intersection of gravity, entropy, and time more starkly than any other objects in the universe. They are not just massive bodies. They are regions where geometry overwhelms every other description. Near a black hole, energy loses its familiar meaning. Time itself begins to behave in ways that defy intuition, and entropy reaches values so enormous that it dwarfs everything else that has ever existed. From the outside, a black hole appears deceptively simple. It is defined by only a few quantities: mass, spin, and charge. All other details vanish behind the horizon. But this simplicity is misleading. It is not a lack of complexity. It is complexity hidden by geometry. The horizon of a black hole is not a physical surface. It is a boundary in space-time, a line beyond which events cannot influence the outside universe. Once something crosses that boundary, its future is no longer part of the same causal story. Information becomes inaccessible, and that inaccessibility is the source of the black hole's extraordinary entropy. The entropy of a black hole is not proportional to its volume, as it would be for ordinary matter. It is proportional to the area of its horizon. This fact alone shattered old assumptions about what entropy measures. It suggested that the true degrees of freedom of space-time are encoded on surfaces, not in volumes. Geometry, information, and entropy collapsed into a single concept. This has a profound implication for time. From the perspective of an outside observer, anything falling toward a black hole appears to slow down. Clocks tick more and more slowly as they approach the horizon. Light stretches, signals fade, time seems to freeze. But this freezing is not an illusion. It is geometry asserting itself. The structure of space-time near the horizon reshapes time so severely that the future of the falling object no longer aligns with the future of the outside universe. One history splits into two. Energy does not cause this. Energy cannot explain it. No amount of fuel or force accounts for time slowing to a halt at a boundary defined purely by geometry. Gravity does. Inside the black hole, the roles of space and time reverse. What was once a spatial direction becomes inevitable future. Falling inward is not motion through space, it is motion through time. Once again, gravity is not acting within time. It is redefining what time means. This is why black holes represent the ultimate test of the idea that energy runs the universe. Near a black hole, energy becomes secondary. Objects fall regardless of their energy. Light bends regardless of its frequency. Even vacuum fluctuations are reshaped by the geometry. What matters is not how much energy something has, but where it is allowed to exist in space-time. Entropy reaches its maximum expression here. A A black hole represents the most entropic object possible for a given size. It is not disordered in the usual sense. It is informationally saturated. There are more microscopic states consistent with a black hole than with any other configuration of matter. This tells us something crucial. The endpoint of gravitational evolution is not energetic equilibrium. It is informational equilibrium. Gravity drives systems towards states that maximize entropy by hiding information behind horizons. Time's arrow points toward these states because there are overwhelmingly more ways to approach them than to avoid them. Energy conservation still holds locally, but it loses its explanatory power. You cannot explain a black hole by tracking energy flows. You must track geometry and information. This reinforces the central theme that has been building throughout this chapter. Gravity is not powered by energy. It is not limited by energy. It defines the conditions under which energy can be discussed at all. Black holes do not burn fuel. They do not shine because of energy expenditure. They persist because geometry persists. Their influence does not fade because nothing is being consumed. Time behaves strangely near black holes because gravity is shaping it directly. Entropy explodes because information is being reorganized. Energy plays a role, but it is no longer in control. Seen this way, black holes are not anomalies. They are revelations. They show us what happens when gravity is allowed to dominate without interference. They show us a universe where geometry, entropy, and time are inseparable, and where energy becomes a bookkeeping tool rather than a driver. If gravity can shape time so completely in these extreme environments, then it is difficult to argue that gravity is merely acting within time elsewhere. The difference is one of degree, not kind. Gravity always shapes time. Black holes simply make that fact unavoidable. This leads to a final realization. If gravity governs time's behavior, and if time governs the meaning of energy, then energy cannot be the foundation of reality. It is built on top of something deeper. The universe does not tick because energy is flowing. Energy flows because the universe ticks, and the ticking itself is shaped by gravity. Black holes force us to confront a truth that is easy to ignore elsewhere. Time is not universal. It is not a single river flowing the same way everywhere. It is shaped, stretched, and in some regions nearly extinguished by gravity itself. Near a horizon, time slows to a crawl. At the horizon, from an external perspective, it effectively stops. Beyond it, the very meaning of future and past is rewritten. This behavior cannot be explained by energy loss or energy flow. No engine is running slower. No fuel is being drained. The clock does not falter because it lacks power. It falters because the geometry that defines time has changed. This is the most direct evidence that gravity does not merely influence events in time, it participates in defining time itself. If time were fundamental and gravity merely acted within it, then time should remain immune to gravity's effects. But it does not. Time bends. Time stretches. Time fragments. These are not side effects. They are central predictions, confirmed by observation and measurement. Gravity and time are inseparable. Once this is accepted, the final illusion surrounding energy begins to dissolve. Energy depends on time for its definition. Power is energy per unit time. Motion is change per unit time. Conservation laws rely on time symmetry. If time itself is shaped by gravity, then energy cannot sit beneath gravity as a deeper cause. Energy becomes contextual. It is defined within a space-time that gravity structures. Change the structure, and the meaning of energy changes with it. This is why global energy conservation fails in an expanding universe. It is not a flaw in physics. It is a clue. Energy is not fundamental enough to be conserved everywhere. Gravity, by contrast, remains well-defined even when energy accounting breaks down. Curvature persists. Geometry evolves. paths remain constrained. The rules stay intact even when the bookkeeping becomes ambiguous. This distinction matters because it reveals what kind of thing gravity truly is. It is not a substance. It is not a fuel. It is not something that flows or depletes. It is a rule about relationships, a rule about how distances, durations, and causal connections are organized. Energy moves things around within those rules. Entropy gives those movements direction. Gravity determines what movements are possible at all. Seen this way, the universe is not burning its way through existence. It is not winding down like a clock. It is unfolding according to constraints that do not wear out. Change happens because probability demands it, and geometry allows it. Time feels real because gravity gives it structure. Motion feels necessary because gradients exist. Energy feels powerful because it governs local change. But none of these are the foundation. The foundation is the rule set that makes them meaningful. This is why gravity persists when energy degrades. It is why black holes remain long after energetic fireworks have faded. It is why the universe continues to evolve even as usable energy declines. The rules do not depend on the fuel. By the end of this chapter, the answer to the original question has sharpened. The universe does not run on energy. Energy does not power time. Energy does not drive gravity. Energy is a language we use to describe change within a framework that gravity provides. Gravity is not the engine. It is the rule that defines what an engine could even be. And once that is understood, the next step becomes unavoidable. If energy can freeze while gravity remains, then we must imagine a universe where energy flow stops entirely, yet structure and motion persist. That thought experiment reveals more than any equation ever could. Is to strip reality down to its barest structure. No heat moves from hot to cold. No radiation streams outward from stars. No chemical reactions proceed. Every familiar process that depends on energy exchange is silent. At first glance, such a universe sounds indistinguishable from death. But that intuition comes from confusing animation with structure. Energy animates, gravity structures. Even in a universe where energy flow is frozen, space-time would still possess geometry. Distances would still exist. Time would still be ordered. Causal relationships would remain intact. Objects would still have world lines, paths through space-time that define what can influence what. Nothing would be happening in the energetic sense, but everything would still be constrained. This distinction is subtle but decisive. Energy flow is about processes. Gravity is about permission. In such a universe, a particle placed near a massive object would still exist on a curved space-time background. The straightest path available to it would still be defined by that curvature. Even if no kinetic energy were being exchanged, the geometry would still dictate where motion would occur if motion were allowed. The rules would still be written, even if the play were paused. This thought experiment exposes a category error we rarely notice. We often assume that without energy, nothing meaningful remains. But meaning in physics does not come from activity alone. It comes from structure. A chessboard does not stop being a chessboard when no pieces are moving. The rules still exist. The possible games are still defined. Gravity is the chessboard of the universe. Even without energy flow, time ordering would still exist. Events would still be earlier or later. Cause would still precede effect. The arrow of time would be muted, but not erased conceptually. The universe would not be evolving, but it would still have a structure within which evolution could resume. This reveals something profound about gravity's independence from energy. Geometry does not require motion to exist. It does not require fuel. It does not require expenditure. Once established, it defines a space of possibilities, regardless of whether those possibilities are currently being explored. Energy, by contrast, is meaningless without time and structure. Energy is defined by change. Without allowed change, energy becomes a static label. It loses its role as a driver and becomes a descriptor waiting for motion to resume. This asymmetry tells us which concept sits deeper. Gravity can exist without energy flow. Energy cannot exist meaningfully without gravity and time. The universe we inhabit is not static, of course. Energy flows everywhere. Stars shine, heat spreads, entropy increases. But the fact that we can coherently imagine a universe where energy is frozen while gravity remains tells us something essential. Gravity is not dependent on energy in the way engines depend on fuel. This is why gravity survives in the long run. As the universe ages, usable energy declines. Stars burn out. Temperature differences fade. Eventually, energetic processes will become rare, but curvature will remain. Space-time will still be shaped by whatever mass and structure persists. The rules will still be there, even when the action slows to a whisper. This directly challenges the idea of a heat death as total nothingness. Heat death is the end of energetic activity, not the end of structure. Geometry does not vanish at equilibrium. It becomes quiet, not absent. In such a future, gravity would still define horizons, distances, and causal limits. Black holes would still exist. Time would still be ordered, even if nothing interesting were happening within it. The universe would not be powered, but it would still be governed. This clarifies the original question more sharply than ever. If the universe can exist coherently, without energy flow, but not without gravity, then energy cannot be the thing that runs it. Energy animates the story, but gravity writes the script. At this point, only one class of objects remains to be examined, the ones where energy fades into irrelevance and gravity dominates completely. Objects where entropy is maximized, information is hidden, and geometry becomes absolute. Black holes. They are not just extreme objects. They are the logical conclusion of everything we have been following. Objects in the universe. They are the places where our usual hierarchy of explanations collapses. Energy, force, and even particles lose their familiar roles. What remains is geometry, entropy, and information, stripped to their essence. If gravity is not fuel but rule, then black holes are the clearest expression of that rule taken to its limit. Every path that gravity carves through the universe seems to lead inevitably toward black holes. Stars form because gravity compresses matter. Stars die because gravity overwhelms the energy that once held them up. Galaxies evolve under gravity's guidance, funneling matter inward over cosmic time. When collapse proceeds far enough, nothing can stop it. Energy does not fail because it runs out. It fails because geometry no longer permits resistance. This is the first crucial clue. Black holes do not form because energy is exhausted. They form because space-time geometry becomes so curved that no configuration of energy can prevent further collapse. The rules change. What was once optional becomes inevitable. At the horizon of a black hole, gravity no longer behaves like an interaction among many. It becomes absolute. All future directed paths point inward. This is not a force pulling objects in. It is the structure of space-time removing every alternative. Falling is no longer motion through space. It is motion toward the future. Energy loses its familiar meaning here. An object with enormous energy and one with almost none cross the horizon in the same way. Light and matter are treated equally. The geometry does not ask how much energy something has. It only asks whether a path exists. Inside the horizon, it does not. This indifference to energy is profound. If energy truly ran the universe, then the most extreme regions should be dominated by energetic effects. Instead, they are dominated by geometric ones. The closer you get to a black hole, the less energy matters and the more structure matters. Entropy, however, explodes. A black hole possesses more entropy than any other object of comparable size. Its entropy is not stored in the motion of particles or the distribution of heat. It is stored in geometry itself. The area of the horizon encodes an enormous number of possible microscopic states. Information is not destroyed. It is hidden by structure. This is a critical distinction. Entropy here does not arise from energy dispersing. It arises from information becoming inaccessible. The horizon divides what can be known from what cannot. Probability space expands dramatically because countless internal configurations correspond to the same external appearance. Once again, gravity is not spending energy. It is creating constraints. The entropy of a black hole grows because geometry limits access, not because energy is being used up. Time behaves accordingly. From the perspective of an outside observer, processes near the horizon slow and fade. Clocks tick ever more slowly. Signals stretch and redshift. Time itself seems to dissolve at the boundary. This is not because energy is being drained from clocks. It is because the definition of time is changing. Inside the horizon, time and space exchange roles. Moving inward is not a choice. It is the future. No amount of energy can change that. No fuel can reverse it. Geometry has spoken. Black holes therefore reveal the ultimate hierarchy. Energy cannot overpower gravity. Energy cannot escape geometry. Entropy is maximized not by energetic chaos, but by informational concealment. Time bends, not because processes slow down, but because space-time dictates a new order. Seen this way, black holes are not anomalies. They are confirmations. They show what happens when gravity is allowed to define reality without interference. They show a universe where energy is secondary, entropy is dominant, and geometry is law. If gravity were fuel, black holes would consume it. They do not. If gravity were energy, it would have to be localized. It is not. If gravity were an interaction like the others, it would weaken or saturate. It does neither. Black holes persist because rules persist. They remain long after energetic processes have faded. They continue to define horizons, causal structure, and entropy budgets long after stars have burned out. They are not engines. They are endpoints of structure. This makes them the most honest witnesses in the universe. They do not allow comforting metaphors. They force us to confront what truly matters when everything else is stripped away. And what remains is not energy. It is geometry. Black holes also force us to confront the ultimate fate of information and time. In ordinary systems, entropy increases because information spreads out. Heat diffuses. Details are lost in the noise. In a black hole, information does not spread. It disappears behind a boundary. And yet entropy still increases. This tells us something startling. Entropy is not fundamentally about energy dispersal. It is about information becoming inaccessible. This distinction matters because it reveals gravity's true power. Gravity does not need to move energy around to increase entropy. It only needs to reshape what can be known. By creating horizons, gravity maximizes entropy more efficiently than any energetic process ever could. The universe becomes more probable, not because energy is scattered, but because geometry hides detail. This is why black hole entropy dwarfs all other entropy in the universe. A single black hole can contain more entropy than all stars, gas, and radiation combined. This is not because it is hot or chaotic. It is because its geometry allows an enormous number of internal configurations to correspond to the same external appearance. Energy becomes irrelevant to this counting. The entropy depends on area, not on energy content in the usual sense. Geometry alone determines the number of possible states. Time responds accordingly. Outside the horizon, time slows. Inside, time points inward. Across the boundary, time loses its continuity. There is no global clock that covers both regions. Gravity has fragmented time itself. This behavior makes it impossible to argue that energy underlies time. Energy relies on time to be defined. A quantity per unit time has no meaning if time itself is ambiguous. Near a black hole, energy descriptions still work locally, but they lose global coherence. Geometry does not. Once again, gravity proves deeper. If energy were the engine of reality, black holes would represent failure. Engines fail when fuel is gone. Black holes do not fail. They persist. They define structure long after energetic processes have ended. They are not powered, they are enforced. This persistence carries profound implications for the ultimate fate of the universe. As stars fade and energy gradients flatten, black holes remain. They slowly evaporate over unimaginably long timescales, but even that process is governed by geometry and horizons, not by traditional fuel consumption. The evaporation is not an engine running down. It is information leaking through structure. When the last black hole finally dissolves, the universe will not end because energy ran out. It will end because structure relaxed. Geometry will approach uniformity. Only then will time itself lose its meaning entirely. This reveals the final hierarchy with brutal clarity. Energy is temporary. Entropy is directional. Gravity is structural. Energy burns out. Entropy evens out. Gravity remains until nothing is left for it to shape. By the end of this chapter, the conclusion is unavoidable. If we want to know what truly runs the universe, we must stop looking for fuel. We must stop imagining engines. We must stop projecting our local experience onto the cosmos. The universe is not powered forward. It is constrained forward. Gravity does not act because energy tells it to. Energy acts because gravity allows it to. And with that realization, we are finally prepared to state the answer plainly, without metaphor and without comfort. Gravity is not the fuel of the universe, it is the rule. Black holes also reveal something even more unsettling. They show that energy is not only secondary, but sometimes almost irrelevant to what ultimately defines reality. Near a black hole, you can pour in energy, remove energy, radiate energy away, and none of it changes the essential fact that geometry dominates everything. The horizon remains. The causal structure remains. The future remains pointed inward. This is the final failure of the engine metaphor. An engine responds to input. Add fuel and behavior changes. Remove fuel and motion stops. A black hole does neither. Once formed, it does not care how much energy approaches it. It does not speed up or slow down its essential role. It does not adjust its authority. Geometry has already won. Even the most energetic particles in the universe, cosmic rays moving at nearly the speed of light, become indistinguishable from the weakest particles once they cross the horizon. Their energy does not grant them privilege. Their trajectory is dictated entirely by space-time structure. This is not how a fuel-driven system behaves. This is how rules behave. The dominance of gravity over energy becomes absolute here. Energy can no longer buy freedom. Momentum cannot negotiate escape. No amount of power alters the outcome. The future is geometrically fixed. Entropy reinforces this conclusion. The growth of black hole entropy does not depend on the energy of what falls in, only on the increase in horizon area. A low energy particle and a high energy particle contribute to entropy in the same fundamental way. What matters is not how much energy enters, but how geometry changes to accommodate hidden information. This destroys the last intuition that energy might secretly be in charge. If energy were the ultimate currency, then the most extreme environments would be ruled by it. Instead, the most extreme environments ignore it. Time itself bows to geometry here. From the outside, time slows until processes appear frozen. From the inside, time points inevitably toward the singular future. There is no energetic explanation for this behavior. There is only structural inevitability. This is why black holes have become central to every serious attempt to understand the foundations of physics. They are not exotic curiosities. They are clarity machines. They strip away comfortable assumptions and leave only what cannot be denied. And what cannot be denied is this. When gravity is allowed to dominate fully, energy becomes descriptive, not causal. Entropy becomes overwhelming, not gradual. Time becomes conditional, not universal. Black holes are therefore not the end of physics. They are the end of a misunderstanding. They show us that the universe is not sustained by consumption. It is sustained by constraint. Reality does not persist because something is being spent. It persists because the rules remain consistent. Energy moves things around within those rules. Entropy tells those movements which way to go. Gravity defines which movements are even possible. That is why black holes persist long after energetic fireworks have faded. That is why their influence does not weaken. That is why they dominate the entropy budget of the cosmos. That is why they reshape time itself. They are not engines, they are enforcement. By the end of this chapter, the hierarchy is no longer ambiguous. Energy does not run the universe. Energy runs inside the universe. Gravity runs the rules of the universe. And once that is accepted, the final synthesis becomes inevitable. If gravity is not fuel, not force, not even fundamental interaction in the usual sense, then what it truly represents is something far deeper. The definition of what can happen at all. Searched for the engine of reality. We have assumed that somewhere beneath motion, beneath change, beneath time itself, there must be something being spent, some reservoir slowly draining, some fuel burning away to keep the universe alive. Energy fit that intuition perfectly. It could be counted. It could be conserved. It could be transformed. It behaved like currency. And so we treated it as cause rather than description. But everything we have uncovered points in the opposite direction. Energy does not explain why the universe has structure. It does not explain why time has an arrow. It does not explain why gravity persists without loss. It does not explain why black holes dominate entropy. It does not explain why motion continues even as usable energy declines. Energy explains how things move once the rules already exist. It does not explain why the rules exist at all. Gravity does. Gravity does not behave like fuel because it is not fuel. It does not get used up. It does not flow from place to place. It does not decay with time. It does not obey the same accounting rules as energy because it is not part of the accounting. It is the framework that makes accounting possible. Gravity defines geometry. Geometry defines distance and duration. Distance and duration define motion. Motion defines energy. Energy is downstream. This is the inversion that changes everything. The universe is not powered forward, it is constrained forward. It unfolds because probability is explored within a structure that does not wear out. Change happens not because something is being spent, but because something is allowed. Entropy gives direction. Gravity gives structure. Energy traces the path. Once this hierarchy is seen clearly, many long-standing confusions dissolve. The failure to localize gravitational energy is no longer a problem. It is a feature. The ambiguity of global energy conservation is no longer troubling. It is expected. The dominance of black hole entropy is no longer mysterious. It is inevitable. Black holes do not represent places where physics breaks down. They represent places where the true hierarchy is revealed, where energy loses authority, where geometry and information take over completely, where time itself bends to structure rather than flow. In that extreme, gravity shows its true nature, not as an interaction among others, but as the rule set that governs them all. This is why gravity feels different. This is why it resists quantization. This is why it refuses to behave like a field carrying energy. This is why it shapes time rather than existing within it. Gravity is not a thing inside the universe. It is the condition that allows a universe to exist. Energy burns out. Entropy evens out. But gravity remains, not as force, not as fuel, but as constraint. The universe will one day reach a state where stars no longer shine, where temperatures equalize, where energetic processes fall silent. But geometry will still exist. Causal structure will still exist. Horizons will still define what can be known. The rules will still be written, even if the story has grown quiet. This is the deepest answer to the question we began with. The universe does not run on energy. Energy moves things. Entropy gives direction. Gravity creates the stage where both can exist. Gravity does not power the universe. It defines what power means. If gravity defines the rules rather than supplying fuel, then many of our most familiar metaphors about the universe quietly collapse. The idea of the cosmos as a machine winding down assumes something essential is being consumed. But rules do not wind down. Constraints do not fatigue. Geometry does not age in the way engines do. What changes is not the framework, but what unfolds within it. This is why the future of the universe is so often misunderstood. When physicists speak of the end of stars, the cooling of space, or the decline of usable energy, it is tempting to imagine the universe itself dying. But what is ending is activity, not structure. Processes fade, gradients flatten, entropy approaches its maximum. Yet space-time does not vanish. Causality does not dissolve. Gravity does not switch off. Even in the quietest possible future, geometry still defines distance. Time is still ordered, even if nothing interesting happens within it. Horizons may still exist. Black holes may still shape causal boundaries for unimaginably long durations. The universe does not stop because energy is gone. It becomes silent because probability has been exhausted. This distinction is subtle but essential. Energy exhaustion is not existential. It is descriptive. It tells us what kinds of processes are still available, not whether reality itself continues. Once this is understood, the conservation of energy takes on a new meaning. It is no longer the ultimate safeguard of existence. It is a consequence of symmetry within a stable geometric framework. When that framework changes, as it does in an expanding universe, the bookkeeping changes with it. The rules remain, but the accounting adapts. This explains why global energy conservation fails in cosmology without threatening consistency. Energy is conserved where space-time symmetries allow it. Where they do not, energy loses its absolute meaning. Geometry does not. Gravity's persistence is therefore not mysterious. It is expected. As long as there is structure, there are constraints. As long as there are constraints, there is gravity in some form. Energy may fade, but the relationships it once governed remain defined. This perspective also reframes the search for deeper theories. The goal is no longer to find what gravity is made of in the same sense as particles or fields. The goal is to understand why these rules exist at all, why information arranges itself into geometry, why probability takes the form of space-time. These are not questions about fuel, they are questions about logic. The universe, at its deepest level, behaves less like a machine and more like a consistent mathematical structure. Things happen not because something pushes them, but because certain transitions are allowed and others are forbidden. Reality unfolds because it can. Energy gives us a way to measure change within that unfolding. Entropy tells us which changes dominate. Gravity tells us which changes are possible. This is why gravity feels timeless, not eternal in a mystical sense, but indifferent to the flow of events. It does not care how much has happened. It does not keep score. It simply constrains. Once we let go of the need for an engine, the universe becomes simpler, not more complicated. We stop asking what powers reality and begin asking what defines it. The answer is no longer something that burns, but something that limits. And that realization prepares us for the final step, the quiet conclusion that follows naturally from everything that came before. What remains, once every metaphor of fuel and engine has been stripped away, is a universe that does not need to be pushed forward to exist. It exists because it is internally consistent, because its rules do not contradict themselves, because its structure allows change without requiring consumption. This is the final inversion that makes sense of everything that came before. Energy does not keep the universe alive. The universe is alive to energy because gravity and structure allow it to be defined at all. Energy is a tool, not a source, a language, not an origin. When we say energy drives motion, we are describing what happens inside the rules. When we say entropy drives time, we are describing how probability unfolds inside the rules. When we say gravity governs the universe, we are describing the rules themselves. This is why gravity refuses to behave like anything else. It cannot be localized, it cannot be spent, it cannot be shielded, it cannot be turned off. These are not failures of understanding. They are clues that gravity was never meant to be treated as a resource. Gravity is constraint. It tells matter how it may arrange itself. It tells light which paths exist. It tells time how it may flow. It tells energy what it means to be conserved and where that conservation applies. Nothing else in physics plays this role. Once this is seen, the original question sounds different. Could the universe run on gravity instead of energy? The answer is no, but not because gravity is weaker or less important. The answer is no, because gravity is not something that runs. Gravity does not operate the universe. Gravity defines it. Energy burns out. Entropy evens out. Stars fade. Temperatures equalize. Processes end. But none of that touches the rules. The universe does not collapse into nothingness when activity ceases. It settles into silence within a structure that remains intact. Even the ultimate future, long after the last light has faded, is not a breakdown. It is an equilibrium within geometry, a quiet state, where probability has nowhere left to go, but where distances, durations, and causal relations are still defined. Reality does not end when fuel is gone. It ends only when structure loses meaning, and gravity is the structure. This is why gravity dominates the deepest questions about existence. Not because it is strong, but because it is unavoidable. Not because it acts, but because it constrains. Not because it moves things, but because it decides what movement means. The universe does not run on energy. Energy moves things. Entropy gives direction. Gravity creates the stage where both can exist. Energy burns out. Entropy evens out. But gravity remains, not as fuel, but as the rule that allows anything to happen at all.